C++ has so many different kinds of built-in data types. We have integers, floating point numbers, characters, booleans, void, arrays, classes, structs, enumerations, all different kinds of built-in data types. But before we can go over the primitive data types in depth, we have to go over this question first. What is a data type? Hey everyone, I'm Sophia. I'm a certified computer science tutor who's taught over 200 students how to code, and I'm here to fill in the gaps and clear up any confusion you have about C++. Alright, so what is a data type? Well, you might have seen a variable created like this before in C++. Now the second half of that looks familiar to math, x equals 4, but in C++ there's an extra word in the front, int. Now this word int is our data type. It's telling the computer two different things. The first one is what type of information we're storing, and the second one is how much memory needs to be reserved in order to store it. So in this example specifically, int is telling the computer that we are storing a whole number, 4, and that we need to reserve 4 bytes of memory for it because it's an integer. Now, before we talk about specific data types, let's take a second and talk about how the computer actually stores this information and what it means to reserve memory. When we count using a single digit from our number system, the decimal system, we can go from 0 to 9. That's because our system is in base 10, meaning we have 10 different digits to work from. But computers use a system called binary, which is in base 2, meaning that each digit can only be a 0 or a 1. This single binary digit is called a bit, and when you group 8 bits together, you get what's called a byte. This is the basic unit of memory in your computer, and it's how information is stored. You can imagine memory as a long row of zeros. When you create a variable, the computer turns some of these zeros into a specific pattern of ones and zeros to represent your value. And depending on the type of value you are storing, the computer will need more or fewer bytes. Now let's start going through these data types one by one. First up, we have integers, or an int. Now integers store positive or negative whole numbers, like 0, 25, -100, or 1000. And by default, integers are signed, meaning they can either be positive or negative. They have a positive sign or a negative sign. But they have a limit. You can only store values within a certain range. So how does this work? Every time you create a variable, the computer stores it in memory using binary, those zeros and ones we were talking about earlier. The number of bits you are given determines how many different values you can represent with them. We as humans can understand binary, and here is how we figure out how many different values a certain number of bits can store. If you take the number of bits and plug it into the formula 2 to the n minus 1, you get the highest number you can store with that many bits. Let me show you. If I have 2 bits, I can count like this: 0, 1, 2, 3. That's 2 bits, 4 total values counting from 0 to 3. So 2 to the nth power minus 1 will equal 2 squared minus 1, which equals 4 minus 1, which equals 3. 3 is the maximum number I can store with 2 bits. The same principle applies when we're working with a larger number of bits, which we're going to look at with our integer data type. Integers reserve 4 bytes of memory, and since there are 8 bits per byte, that gives us 32 bits total. Now with signed integers, you need one of those bits, specifically the leftmost bit or the high order bit, to reserve the sign of the value, whether or not it's a positive value or a negative value. That leaves 31 bits remaining to store the actual number. So for our minimum range, we use a formula -2 to the n minus 1, where n is equal to 32, because that's how many bits total we have, 32 bits. Now we're using n minus 1 because one of these bits is being used for the sign, so we only have 31 bits to store the actual number. Now we're doing 2 to the power of 31 because each bit has 2 different possibilities, 0 or 1. And since we're trying to find the minimum value, we need to make this negative. So our final number is -2,147,483,648. Our maximum range is very similar. We're taking 2 to the n minus 1 minus 1 for a grand total of 2,147,483,647. Now, you might be wondering why that maximum number is one less than our minimum number. And it's not actually. You see, our minimum range goes from -1 to our minimum number, and our maximum range goes from 0 to our max minus 1. Think of it on a smaller scale. There are 5 numbers between -1 and -5, but there are also 5 numbers between 0 and 4. I'm just starting on a different number. The same thing happens on the large scale. You see, integers include 0, and so our positive range gets shifted down one number. So it looks like the maximum number is one less, but it's not. We're just starting at 0 instead of 1. So a variable of type int that's signed would look like this. Int x equals 4, or whatever your whole number value is. Now don't worry, you're not the one converting everything into binary. The computer is doing that for you every time you use a data type. I'm simply teaching you how to do this manually so that you understand what's happening behind the scenes. But at the end of this video, I'm going to show you how to use C++ code to calculate these same limits. Now, if you know that your variable is not going to store any negative numbers, you can modify this data type to what's called an unsigned integer. An unsigned integer only stores positive whole numbers. It still reserves 4 bytes of memory, which is 32 bits, but now that leftmost bit is not dedicated to holding the sign, whether it's a positive or negative number, because now we're only dealing with positive whole numbers. So to find the new range of this unsigned integer, we would be going from 0, because they're only positive numbers, to 2 to the nth power minus 1, where n is 32. We now have all 32 bits available to us to store the actual number. Again, it's -1 because we're starting at 0 and not 1. So we'll have a final number of 4.29 billion, which was double the amount that we had before because now we're not including negative values. So an unsigned variable would look like one of these two examples. You can either write unsigned int variable equals value or just unsigned variable equals value. By default, if you just write unsigned, the computer will know it's for an integer, but as you'll see in the next couple of data types, we can also use unsigned with those as well. So my recommendation is that you put the int just to specify what you're using. Our next data type is called a short, and it's actually just a modification of this integer data type. Shorts store positive or negative whole numbers, but they don't reserve as much memory for it as integers do. Shorts reserve 2 bytes of memory, unlike integers which reserved 4 bytes of memory. So we have 2 bytes, which is equal to 16 bits. Now, like integers, the default for a short is being signed, which means we can have both positive and negative values. That means that leftmost bit is reserved for the sign of the value, whether or not it's a positive number or a negative number. That leaves 15 bits remaining to store the actual number. So to find the limit of a signed short, it's the same way as finding the limit of a signed integer. The minimum value, we take -2 to the n minus 1, which is going to be -2 to the 15th power because we only have 15 bits available to us. That'll end up giving us -32,768. To find the max, it's the same thing. 2 to the n minus 1 minus 1, because we're going to start at 0 and not 1, which will give us 2 to the 15th power minus 1, which is 32,767. So in order to use a short, you just have to pick a value that's between this range, -32,768 and +32,767. If we go past this, we'll get an overflow. So if you want to use a short, just be sure that your value will not go past this number. So to write a variable of type short, you can do it one of two ways. Short int variable equals value, or just short variable equals value. Again, short is a modification of the integer data type. So we're saying a shorter version of integer. That's why it's a short int. And just like integers, shorts can be unsigned as well, meaning they only store positive numbers. They still reserve 2 bytes of memory, which is 16 bits, but now that leftmost bit is not dedicated to holding the sign of the value anymore, leaving all 16 bits available to store the actual number. So to find our new range, we're going to be going from 0, because we're only storing positive numbers, to our new max of 2 to the n minus 1, where n is equal to 16 bits. So this will give us a new max of 65,535. So instead of our range being split between positive and negative values, we have one solid positive range. So an unsigned short could look like this. Unsigned short int variable equals value, or unsigned short variable equals value. Again, when we use short, it's interpreted that it's a shorter version of integer, and we're just saying that it's unsigned, meaning it's only going to store positive values. Moving on, we have a long next, which is yet again another modification of the integer data type. Longs also store positive or negative whole numbers, and their default is being signed. Now here's where things get a little interesting. Long is only guaranteed to reserve at least 4 bytes of memory, the same size as an integer. Well, why is this? Quick history lesson. Back in the 70s and 80s, computers used 16-bit architecture, and integers only reserved 2 bytes of memory, which simply wasn't large enough for many programs. So they introduced the long data type to reserve 4 bytes of memory for the larger numbers. Fast forward to now, though, most systems use 32 or 64-bit architecture, so int was upgraded to reserve 4 bytes of memory. Short was created to reserve the original 2 bytes, and long was sort of just left alone. Because of that, long isn't used as often anymore. Most people just use int, since on most modern systems, int and long are the same size. And yes, you can use long as signed or unsigned, but again, long isn't commonly used anymore. If you did want to use a long variable, these are what the variables would look like. Long int variable equals value, or just long variable equals value. The same principle applies, and if you were using an unsigned long, you would just add the word unsigned in the front. Now, what do you do when you have a number that's larger than what an integer or a long can hold? Well, you guessed it, there is something called a long. This is the last modification of the integer data type, and it also stores positive or negative whole numbers, with its default being signed, and it reserves 8 bytes of memory, double the size of a long. Clearly, they spent months coming up with this name. The range of a signed long is -9 quintillion to +9 quintillion. And if we were doing an unsigned long, it would be from 0 to 18 quintillion. So this data type stores very large numbers. So if you know that you do not need a number that big to store, just stick with the smaller data types, because otherwise you're just wasting memory. And again, a variable for this data type looks like this. Now, we've spent a lot of time talking about whole numbers and all the different ways you can modify an integer data type. Now let's switch gears and talk about decimal numbers. Thankfully, it's a lot more simple. There are only 2 main data types for decimals, a float and a double. A float stores positive or negative decimal numbers, like 7.1, 125.25, or 99.9999. Unlike integers, floats don't have an unsigned version. They can only be signed. In terms of memory, floats reserve 4 bytes, which we said is 32 bits. Floats store numbers differently than integers, though. Instead of storing one whole number, we're breaking the binary number into 3 different parts. 1 bit for the sign, whether it's a positive number or a negative number, 8 bits for the exponent, and 23 bits for something called the mantissa. This format is called IEEE 754 single precision. Now, this is a little too complicated to explain in this video, but it works very similarly to scientific notation. It stores your number in the form positive or negative mantissa, or a base number, times 2 to the exponent. With the computer storing decimals in this way, we can store not only really large decimals, but really small decimals as well. For example, a float can store a minimum value of around 1.2 times 10 to the negative 38, and a maximum number of around 3.4 times 10 to the 38th power. Now, floats can store 6 to 7 digits accurately before any rounding errors tend to show up, so this has less precision than what a double will have. Doubles are really similar. They still store positive or negative decimal numbers, with it always being signed, but they reserve 8 bytes of memory instead of 4, giving us 64 bits total. Now, as splitting up the binary number, we still have 1 bit for the sign, whether or not it's a positive or negative number, but now we have 11 bits for the exponent and 52 bits for the mantissa. And this is called IEEE 754 double precision. Doubles can store a minimum number of 2.22 times 10 to the negative 308 with a maximum number of 1.79 times 10 to the 308th power. Much larger numbers. Doubles also have more precision than floats do. We get around 15 to 16 decimal digits of accuracy before any rounding errors tend to set in. Now, when it comes to creating a variable of type float or double, there's one small difference to them in addition to the data type. Now here I've created two different variables, a float and a double. Not only is the data type different, but I'm also including an f at the end of my float value. Now, by default, all decimal numbers are created as a double because doubles have more accuracy when it comes to storing these numbers. Let's look at our double variable first. We are storing a double decimal number inside of a double data type, so everything matches. But if I were to write float x equals 4.0 without the f, I would be storing a double decimal number inside of a float data type. Now, technically this works, it's compatible and your code will run, but we might lose some precision with our number because we're trying to store a 64-bit number and squeeze it inside of a data type that only has 32 bits available to us. Now, if we put that f, it tells the computer that we want to change the default and store our number as a float to begin with, only in 32 bits. That way, when we assign our value to our variable, it fits nicely inside of 32 bits. Now, this f is not required, but it avoids the extra conversion and helps keep things as accurate as possible for what a float can store. All right, we've covered everything from whole numbers to decimal numbers. Now let's move on to something a little different. It's called a Boolean. A Boolean, or a bool, stores just one of two values, true or false. Unlike integers, though, Booleans cannot be modified. You cannot use signed, unsigned, short, or long with them. It's just bool. It reserves 1 byte of memory, which is 8 bits, but it really only needs 1 bit to do its job. False is stored as 0, and true is stored as 1. So why not just use 1 bit? Well, most computers can't access anything smaller than a byte. It's much harder to locate a single random bit. So for efficiency use, Booleans reserve the whole byte and then just uses 1 bit. Here are some examples of what Boolean variables might look like. If you type true, the computer stores it as 1. If you type false, it stores it as 0. But even if you type a number, it still works. Any non-zero value is automatically treated as true in C++. So -3 and 47 would both evaluate to true. While you can assign any number to a Boolean variable, I wouldn't recommend it because the original value is going to get lost. Any non-zero value is going to get converted to 1. So while this does work, I wouldn't recommend it because it's going to look confusing to you and to other people that read your code. I would just stick to true, false, 0, and 1. Now that we've covered Booleans, let's move on to another small but important data type, a char, short for character. A char is used to store a single letter, digit, or symbol, and it's always wrapped in single quotes. So something like a capital A, the number 7, an exclamation point, or the ampersand would work. A char reserves 1 byte, or 8 bits. But here's something cool. All of these characters, these letters, digits, and symbols, are all just numbers under the hood. They come from something called ASCII, A-S-C-I-I. It's a system where each character is mapped to a corresponding number. So for example, the letter capital A is mapped to the number 65, and the letter lowercase a is mapped to the number 97. There's one of two ways you can create a char variable. You can either do char variable equals a character in single quotation marks, or you can do char variable equals the ASCII value. So in this case, I have a capital A for one variable and the number 65 in another variable. If you put these in code and print them out, you'll see that both of them print out a capital letter A. Now, because you can store ASCII values inside of character variables, characters can be signed or unsigned. It's the same way as figuring it out with integers. Signed characters can have a range from -128 to +127, and unsigned characters can have a range from 0 to 255. Now, why would I ever need an unsigned character? Well, if you take a look at the ASCII table, everything from 0 to 127 covers the standard English characters, letters, digits, punctuation, etc. But values from 128 to 255 are where you get into extended ASCII, things like accented letters, symbols, or special characters. Now, extended ASCII isn't part of the official ASCII standard, but it's supported by many systems for international characters. So if you want to use one of those characters, you have to use an unsigned char. Now, whether you store the character or the ASCII value, it will always print out the character. It won't print out the ASCII value unless you explicitly convert the variable into an integer, like this, int variable name. This tells the computer to treat it like a number instead of a character. Moving on to our second to last data type, we have strings. Now, strings are used to store text, which means one or more characters combined together. Instead of using single quotes like a char, strings are wrapped in double quotation marks. For example, string name equals Sophia. Unlike the data types we've talked about so far, strings are not actually a primitive data type. It's a class from the C++ standard library. All this means is before you can use a string data type, you need to include the library at the top of your code. To do that, you just write #include angle brackets with the word string inside of it. Now, the string data type cannot be modified by signed, unsigned, short, or long, but the string itself can be modified and manipulated. There are a lot of built-in methods like .length, .find, and .size that make it really easy to work with text. Now, unlike the other primitive data types, strings do not have a fixed memory size. They usually start off between 24 and 32 bytes, but they can grow depending on how long your text is. Finally, we have one last data type to mention, void. Now, void is a little bit different. It actually means no type or nothing at all. It's not used to store data. In fact, you can't even create a variable of type void. In fact, void is used to indicate the absence of data, and it cannot be modified because it simply means there's nothing here. Now, voids are mostly used in functions, parameters, and pointers. So if this feels a little abstract at the moment, don't worry. It'll make a lot more sense when we start working with some more advanced topics later on. Now that we've gone over all of the primitive data types, let's take a look at them in code. Let's quickly check how much memory each data type reserves. To do that, I don't need any library. All I need to do is type cout, size of, and my data type. So I'll do int, copy that a few times. I'll do float, bool, char, double, and long. I'll save that and run it. And the value that's going to be returned is the number of bytes of memory each data type returns. Now, if we want to check the limits of these data types, the minimum and maximum numbers, we can use two libraries. The first library is #include limits.h, and this is for integer values. So I would just write cout, and then we have different constants like int min. I also have char max. I have unsigned int max. I have short max. And let's do long min. Save that. I can run this again. There we go. And I get the limits for all of these integer data types. Now, if I want to check the minimum and maximum for decimal data types, I do #include float.h. And here it's the same thing, a cout statement with our float constants. I can do float min, float max, and let's do a double minimum. Save that, run it one more time, and here I get my decimal, min, and max numbers. And that concludes our data types video. In the next video, we're going to be going over variables where we'll actually use these data types to store data. If you want a reference for everything we went through today, make sure you grab the free PDF down below in the description that I created. My email's also down there if you have any questions or want to reach out. Thanks for watching, and I'll see you in the next one.